So let me just give you a quick intro. So I look after like data science at Concert AI. So I head the division. So today I want to talk about like how to debug Gen AI, right? Everybody's coming on to Gen AI applications. They want to see how build applications quickly and kind of how we can, when we get stuck, right? So we need to get out quickly. So the idea is how we can like debug a code, debug a Gen AI stack to see what's happening bad and what's not happening good. So first perspective, I'll start with like a few lines. So like this is very famous saying, you only change what you can understand. So if you debug, kind of you know what's happening. And once you kind of understand what's happening, and or I would say if you don't understand, you're unaware of what's happening, then probably you won't know what's out there. So that's why. So when you understand what's happening, you can change it. So the same ideology, when we like know what's happening inside a Gen AI application, we can maybe modify it, we can maybe improve it. So with that thought, I'll just give you like the key agenda for today. So I'll talk about like how to look at an application in general, and kind of how to look into the internals basically, which part is doing what, how to go inside, how to debug basically, and kind of see the key areas. I'll focus on like two key aspects. One, let's say the RAG part, because that is probably is something we need to focus more upon, because we don't have like out of box solution for that. There are lots of things out there, but yeah, none of them work very easily. Second, I'll go into LLMs directly, right? So these decoder LLMs, Gen LLMs, how do you can see? Like it's easy to give a prompt, but from a prompt to look at the answer and just to debug what went wrong, it's like a complex thing, like a black box, right? So how we can look into that? So let me start with it. So I'll start with like a simple enterprise stack, right? In a general application, if you see, you have a user and like enterprise data. So what you want to do is basically like send a question, send a data, and want to solve something. So in general, any industry, they have their own data, right? Own questions to answer based on maybe finance, retail, whatever. They want to solve their own use cases. So for that very same purpose, you want to, let's say, give to like an engine which makes a prompt and kind of, if require, need relevant context. So you'll maybe go to like your database or maybe your internal knowledge base and get documents, right? So that's where RAG comes in. So from companies' enterprise data, you of get relevant documents, build a prompt, make a context, and with everything, you will send it to less than LLM. This LLM could be online, could be offline, like maybe like GPTs or your llamas that can kind of take care of that, or maybe a system of agents, right? Multiple LLMs out there. So if a system like that exists, right, and eventually let's say you send to LLM, you get the answer. So this looks all good. But what if what you asked for and the answer is kind of incorrect, right? What do you do? So that's where kind of people get stuck, because right now, if you look on the world of APIs, right, it's like a black box. So you can't see anything, what's happening inside. You call an API, you get a response. So from that perspective, it's hard to know what's happening inside, and we can't do anything. So that's we want to look at, like how do we open up things. So let's take one by one. So let's say we look at the layer before LLM. In that case, so the key part comes what you send to LLM, right? So there are three parts over there. One, the question, definitely that has to be right, because you're sending a question, it's your question. Then probably documents, right? That's your community documents. So kind of they are also can't be wrong. But the key part, the third, that can go wrong, right? So maybe the context you got or the few shots you got, those may not be right. So we want to see how we can debug that. So this context comes from your RAG system, right? So this RAG is what you want to look at. How do you look at which part of RAG is going bad? So at a high level, I would say RAG has three key components. So I'll just talk about them one by one. How to, I would say, look at the different layers of RAG and look inside. What's working, not working, what did basically didn't work properly. So first is like embedding quality, right? So you're using embedding models to convert your text into embedding vectors. Maybe that's not good quality. There are like 100 models out there. So they are not all good or not capturing the right semantic information you need for your application. Second, maybe your vector store, right? You use chromas, use fairs or whatever, but they're not doing the perfect job. So that could be a second place of issue. Third, data type. So that's more, I would say, on how you manage things, because like on chunks or I would say graphs. So that's let's just debug this, right? Let me expand this for you. So for the same thing, embedding quality. So there are like two main things over here. One, is your embedding model able to differentiate concepts? Like for example, you are talking about, let's say maybe your software works on, let's say, e-commerce data, right? So look at retail, let's say about products. So can it differentiate between, let's say, retail users versus products informations? So that's like the model quality. What's the understanding of the model? How can it differentiate between the concepts? So that's the first part. Second is basically your information aggregation. Like for example, your product review. So that product review contains lots of information. Eventually, the embedding model will take all the words, the content, and summarize into one single vector. So is that aggregation making sense, or kind of like missing out over there? That's the second thing that would go bad. Vector lookup, like there are multiple things over there. One, in a vector store, what happens? These are designed to like make things faster. So in the, I would say, attempt to gain speed, they lose accuracy. So we look at that, how to basically trade off between accuracy and speed over there. Then, like in a vector store, you need some function to compare, like cosine similarity, equivalent distance. So they also have drawbacks. So let's talk about that. What's the impact of those things? Then I would say data type, right? I was telling more towards you like a chunk RAG. You divide a document into chunks, or maybe as a graph. So that's like entire topic in itself. So with this, I would say key idea. I'll try to break up RAG into these, I would say, 6 areas, and see how we can debug the system to see what's going bad in each of these buckets. So let me start with the first one, like embedding quality. Then you go to vector lookup and data type. So talking about the differentiating power of embeddings. So the idea being, if we have these embedding models, how we can judge them? Are we doing the right job or not doing the right job? So let's take a sample, I would say, give you an overview of how the system works. We have documents, right? So from documents, we give to embedding model. So that model creates vectors, right? Which are like bunch of numbers out there. Eventually that goes to your some similarity function, be it cosine, be it whatever. So that function gives you like a similarity metric. So for every vector, you could select this is a number, it's 0.85 closer, 0.89. So it will give you similarity score, whatever function you use. So eventually at a high level, right? So this is what the embedding system is doing. A model gives you embedding, use a function to kind of differentiate. So we can go into each layer to see what's going bad over there. But let me first tell you how to look at the bigger picture, right? For example, end to end. I gave the documents, I got my similarity score back, right? I'll zoom into it later. If I look at the last output, now how can I say that's not working good, right? So to test that, we can do a simple test, right? You can create sentence. So let me show you, like, what I did. Basically, I took 4 categories. So look, right? I took like basically category like food, cars, physics, medical. I took like 7 sentences each of them. You can just read them in a normal sentence, right? So per topic, I just pick any sentences to see, is my model able to differentiate these concepts? So the idea being, as you can see, right, they are very distinct topics with very less overlap. So let's see what does the model do. And you guys read a normal sentence, right? Nothing fancy about them. So to look at them, as I was telling you, I look at the end-to-end picture first. I'll pass it through an embedding model, get the vector, run through, let's say, a cosine similarity, get the score. I'll first look at the end-to-end level, how to see are they good or bad. So this picture looks scary, but let me help you what this looks like. So this is like a 28 cross 28 matrix, the same example I showed you, right? I had 7 sentences for each of the category. So which was like food. So the first 7 are food, then car, then let's say my physics, and then medical, right? So it's the same thing, 7 times 428 cross 28 matrix. So what it shows that how these sentences are similar to each other. Can you look at the axis on the right side, right? So the score of 1 looks fully similar, and bottom is like let's say less similar. So the lighter means they are similar, darker means they are like not similar. So look at one pattern, right? So look at these small squares coming, right? 7 cross 7. So that means at least they are more similar in their own zone, right? In their intra-family, I would say. So that shows this model is better enough, right? So for all of them, I can see like small 7 cross 7 boxes in between. So that means the model at least is able to differentiate between own category. And the good part, let's look at this square, right? This is darker for all the other squares. That means, yes, it's able to differentiate that this category, let's say by medical, different from physics, car, and food. So that's like one high-level view of seeing how your categories are different. And this shading, right, tells you like you see like a shade of like a light pink in between, all those things. That shows you dilution or where it's getting confused. So with like a plot like this, you can quickly create your sample sentences. Like in your industry, you're talking about maybe retail, finance. So in topics which matters more in the industry, create your sentence from domain knowledge and make a chart. So this was made by GPT 3.5. I'll show you one more thing. How do you compare models, right? I'll show you two more similar charts for, I would say, two more models and see how they're better or worse than this, right? So the next one, and I just notice a few things. Like the range right now here is from 1 to zero point 0.7. It's not going to 0. So that means the model is giving score between 0.7 to 1 to all these sentences. That's not a good thing, right? Because you want more definition power. So to get more definition power, we want to see they are more far apart, right? So right now, it is able to like differentiate within them. Like for example, the scores between the cells are more pointed above. That's why they're lighter, but not too far apart from other ones. Look at next one. This is sentence bird. Note over here the range, right, goes from 1 to 0. So that's like a full scale range is covered. So this model is able to cover the full span. Now the shades, although they're still relative, but now the light is very far apart from the dark. In the previous one, it was like 1 to 0.7. Here is 1 to 0. So this model, again, you can see like same 7 squares coming up over here. This was also good, but it is better than previous one because the key part is, see like scores were like that within them are more than 0.5 above, but outer is like 0.1, 0.09. So it is able to differentiate very easily between other sections. That's like one way, a quick way of checking the models, right? How good they are based on the scores that you're looking at. So similarly, I can show you like one more of this. In this like a special case, I took like a domain model, right? It was like a medical domain model. That's like a PubMed bird. It understands only medical language. It does not understand other domain concepts. As you can see, it's like very good on the medical part and cuts off everything else, right? It's dark for everything else, but can't differentiate any of the categories. So sometimes probably for a domain, you need that, right? You don't care about the categories. You only care about your own domain. Like in this my case, I work in medical industry. So to me, this is more important. So this also can be helpful. So depending your area of your work, you can choose whichever fits you. So I'll come to more details of this. Now I'll like do a deep dive inside it, right? So basically, how do we look inside the embeddings? So the easy way to look at the embedding quality is visualize, right? If you can look in front of you, you can see what's good, what's not good, and maybe use your own human judgment to see what's working good, not good. But I'll give like some key points on how to look at embeddings, right? There's something called a manifold or like a lower representation of the data. Like as you know, these dimensions in the embedding vectors like 764 for BERT or like 1000 dimension vectors, you compress to 2 dimension, right? Because as humans, we can look at only 2 and 3 dimensions. So that transformations at times basically manipulates the data views. So what you see may not be exactly what you believe, right? So that's why when you look at manifolds, it has one good properties, right? Like the closer points, they show similar concepts. We want that to happen so that we can know that these are my vectors where I want to be closer and these I want to be far apart. So basically we can check the proximity, right? So in the manifold, the points which are closer are of interest to us and they should be belong to the same class. And this also tells the embedding model's semantic function, right? Like I was telling you about the medical domain. It was making the medical sentence closer, but others far apart. So you can check your own domain to see how that is working for you. Again, I was telling you, these are very high dimensional complex vectors, right? There is lots of math behind to tell you what's working out there and not working. So I would say, take it with a pinch of salt that there are some things which will not work good, like something called cost dimensionality, non-relations. So I can't explain all of them, but like everything is not perfect. So you need to choose your right embedding model to kind of see the relations. I'll give you some pointers, what to choose basically. I would say when you just Google, right, look for this word. Is that manifold distance preserving? Like for example, you names like MDS, multi-dimensional scaling, LLE, locally embedding, your UMAP, right? All these are distance preserving manifolds. That means if the points were far in high dimensions, they are still far 2 dimension, right? If they're close, they're close here now. So at least the picture is not distorted. What you see is the close to reality. It may not be perfect, but yeah, close there. So I'll take example, right? There is some data out there. It's like on the left side, it's a 3-dimensional data, right? You can visualize 3D. I'll convert 3D to 2D, right? Normally we have like 1000 dimension vector, we project to 2D, but I'll project this to 2 dimension to show what's the difference between manifolds. So I'll just cluster them first, right? So that's easier for you to understand, like which are different clusters. There are like 4 different clusters out there. I have different colors to understand. Before I proceed, I've like given the heading global versus local. So as you can understand, like there's some like a global manifold, local manifold, to capture the global sense of the data and local sense. Before I move next, can anybody guess what will come up in a global manifold? So we take a global snapshot in 2D of this version. What do you want to see? Any guesses? Like what kind of structure can you see in this case? Yeah. So like it looks like an S, isn't it? It's a 3DS, right? A 3DS. So global manifold captured that, right? It's actually an MDS transformation of that. So you can actually see an S. Look at again, right? Do you see an S over here? So that basically is the scope of this. It can capture those things. But the key part, can you guess the local one? Any guesses? Local means looking at the neighborhood, right? Look at the picture. What can you guess from that will come in local manifold? Any guesses? Sorry? Okay, anything else? Look at picture again. Any quick guesses? D. Okay, C, D. Anything else? I. Okay. Any more? Right, there are like 4 things. Look at the colors, right? That's why we make them different. Few more seconds. It's actually DHS4. Look at it, right? Can you see D again? Look at data. It's a D in the 3D space, at the H, the S, and the 4. Are you able to connect that back? See, but that's the power, right? Local manifold captured easily. It's algorithm called LLE, locally embedding, right? So to me, that's the power. Same data is in front of you, right? This captures an S, that captures in DHS4. It was out there in the beginning. If you can connect back, right, you can connect dots again, right? That's what's there. But to me, yeah, that's the way you can look at data. So this tells you that your interpretation will change. Like if you look at this manifold, you will look at this part, but if you look at that manifold, you'll see something different. So that's like a clue how you look at embeddings, right? So depending on use case, you want to look at different things. So like in case of, let's say, RAG, right, you want to look at which vectors are closer, like the document vectors. I will look at the local part over there, right, because they have the same meaning. So I will go for the local embedding in that case, right? But we will look at, for example, how different my questions are with the answers. That's a different concept. But for our RAG, I would say focus on the locally embedding ones, right? That gives you a much more, I would say, information out there. Let me take you to the next part, right? So the converse, I was telling you, like, not all manifolds are preserving. Let me show you an example of the other side so that you are aware what's the drawback. TSNE, it is not distance preserving, right? So by definition, it uses like a concept of local graphs. It makes a picture from the local neighborhood, right? So the size you see in a plot doesn't really mean anything, right? Because they're not really reflective of the actual distance over there. Similarly, which are far apart don't mean far. So the algorithm over there basically causes a source of confusion because they have a different function to optimize. They don't really preserve distances. So I would say don't interpret the shapes in such kind of a graphs. So because they kind of like loosely balance between a local aspect and global aspect, they're trying to basically optimize both of them in a single way. It's an algorithm. It's not bad. Different purpose, I would say. So that the variable called perplexity, right? Let me show you the example of that. So this is an example, right? This was the original one, data, and the first plot. It's a simple 2-dimensional plot with 2 clusters over there. If I choose perplexity 2, I see this cluster, right? It's much different from those data. But now if I take a perplexity 100, so you see what you see is much different what was original, right? So basically, just by changing perplexity, the information was twisted or changed in a different way. So kind of what you interpret from this graph would be much different from the original one, right? So that's why I would say TSNE is not a good way to look at embeddings, right? So again, use distance preserving manifolds, right? Which will give you a better idea of how things are kind of working and will help your cause. So I'll come back to my example, right? That food, car, physics, and medical. Earlier I showed you like a confusion matrix, right? Of the distances. Now basically I'm plotting those 28 sentences into embedding, right? This time it's MDS. It's a distance preserving manifold, right? So points which are closer are like actually close in the Handman space also. The far points are far. So as you can see left plot, right? They're all mixed up. Colors represent categories. So what I wanted basically, if these concepts were clear, they would be different, right? More different clusters. So a BERT-based default embedding model is not able to get that, right? So this is like a default BERT embedding model. But if I use something like a sentence BERT, right? Now look at that. So these are very well far apart points, right? So they are kind of able to cluster easily. So again, why these embeddings, you can kind of see what is like good for your domain, which categories are getting different. So like the left one doesn't have a clear concept separation, but the right has that. So you want like a model like that for your own domain, which can differentiate your categories, right? Whichever industry you work in. So I would say you can plot them and look at these metrics, right, to see. I'll move on from this and now talk about the query and retrieval part, right? So that was first part, embedding, how to look at the quality of the embedding model. Now let's look at the retrieval part, right, the query part. So look at the query at the top, right? I like basically took like company report. It was like a Microsoft annual report which I downloaded from internet and asked a question. What are the new projects in recent development happening in the company? So the red circle, right, is my query, embedding of the query vector, right? And the green circle are all my fetch documents. If you look at this plot, right? So kind of the green circles are my documents which the RAG system found for this query, and red represents basically the query. So this plot shows that the points are closer, right? Because it's a distance manifold, it's a local manifold like isomap. So it's a local manifold, distance manifold. So that means it's a good retrieval, right? So just by looking at these maps, you can say, is your RAG doing a good job or not a good job? Let me show you a converse example. Actually, sorry, for this, yeah, this was the real document, right? Look at the green words, like they were asking just development things. So like they're saying they're doing things like cloud computing, AI devices, OS systems. So actually found the good document, right? And similarly, they're talking about computer science, broad range of disciplines. Just leave the text, doesn't matter. But the key point is it actually worked, right? It find the right documents for the questions, and that was also shown in the manifold. The second case, right? The question was, what are company's future plan? Again, red is the query, green are the my documents. They are far apart. So this indicates that my answer may not be relevant, right? So kind of what I get back is not reliable. So this like is lower quality. So you can actually look at these embeddings, right? These manifolds to see, is your system doing what you expect to do or not? So these, I would say, is one way of looking at these informations, right? Your documents, your questions, are they doing good, not doing good? So these plots help you that. Again, in this, I'll show you the actual text, right? Everything is like not related. So don't spend energy to read it. But yeah, it was not relevant, and that's why it was showed in the embedding also. So with this, I'll show the same plot again, right? So the first plot was the good retrieval, right? So the isomap is the same plot over here. I'm showing the same query question which you show on the first slide, right? For the good one in other manifolds, just to show difference between them. So like UMAP, isomap, LLE, and MDS. If you look at the three, like LLE, UMAP, isomap, they're all close by, right? Because it's a good retrieval. But in MDS, it seems far apart, right? So it may seem like that it's not a good thing, but it's the reason being MDS is like an exact global construct. So it looks at the exact distance over there. In reality, the question is a question, right? And those are answers. They are related, but not similar. So that's why MDS tells you, yes, that sentence is not similar, right? So that's why it's far apart. But these local embeddings, they capture that, yeah, there is a relation, and you can check that. You can see like it is kind of giving you some essence of similarity. So local embeddings will give you what you look for in RAG, right? But MDS won't show you what you're looking for. So don't use MDS for RAG systems, right? But there is interesting new encoders coming, like I'll talk about later, called Dual-Encoders, which can also tell you the relation also in embeddings, right? I'll talk to that. That's like a new thing coming from Facebook. It's like a dense page retrieval. So I'll show you how that works. But same thing for the converse example, right? In that case, you see in all the like isomap was far apart. The same thing is apart in all manifolds, right? So anything that is low quality would be different or like far apart in all kind of manifolds. So it's an easy way to see how is your basic quality of the vectors. Are they like close by, far apart? So to me, these manifolds can help you. If you use them properly, you can get the information. So that was like the manifold part. So I was telling you, like all these embedding vectors, right? What are you doing? For every word you get a vector, you have to aggregate it, right? To get like a concise, I would say, representation of the entire document. So that's where this comes in, aggregation. You need to be sure that you use the right thing, right? So if you look at embedding models, there are multiple ways to do something called a mean pooling, right? You have an encoder. So basically give your sentence, and like this is the title of the paper, attention of the read from the authors of BERT, and let's say you give these words to the model. what you get is embeddings. So now you can take a mean of each of the elements, right, and get like a mean pooling, and that's like your sentence embedding. That's like one strategy used by default in many of the modules. So this is the default strategy, use them, but there are more techniques out there to try out. So I'll show you other also. Something is called other is like CLS. The same thing, this time you just took the embedding of the first token. They added a new token called CLS, right? That's like a first start of the sentence token they add in the embeddings to like a use separator. And what their theory is that it's like a blank vector. That means it is taking information of neighborhood. There was nothing inside the token. Whatever was ahead of it, that got basically diluted to itself. It's like a summary in embedding way or semantic way. So that itself is good enough to capture a summary of the entire sentence. So that's like called the CLS pooling way of capturing information, right? So there is a third way called TANH or the pooler vector. So actually this was also given by the founders of this paper, the BERT from Google, but actually they did not mention in the paper. So that's why this is there in the code implementation, but not on the paper. So people tend to forget this in, but this actually works better than CLS. It's like again using CLS, but extra activation on that. So this is like initial way. As a comparison, if you look at them, I look some sample sentences and they are all in high 0.9s, but the TANH takes it more higher. That means the differential power of TANH is better. So the activation function looks at the right neurons and kind of able to differentiate better. So these are choices you can make. You can kind of use each one of them, and normally you'll find mean pooling being used in most of these systems, but you can change it, right? It's just a system out there. So talking about vector indexing. So you know, like there are vector DBs like Chroma, you have other things, FAS, many out there. So people believe it's like just a store, right? You like insert data and look up. But these are like slightly more better. The idea is the vector DB is able to get you more benefit, right, in time. So if you have like a million vectors, you don't scan a million, right? Maybe you scan like maybe a log of that or something of that. So these are some algorithms to make things faster. But in that speed, they compromise some things. So there are like lots of examples. Like for example, you look at Google, there are algorithms like HNSW, hierarchical navigable small graph. This is in Chroma DB, right? Then you have LSH, ELSH, that's used in scan by Google, NSG, IVF, MSTG. There are multiple algorithms out there which are kind of doing those optimization for you to have a faster lookup. So to give you an idea how they are working basically and kind of how they trade off between speed and this, I'll pick one called LSH, right, to give you an intuition how this works. So let's say you have a normal 2D space, you take like a random vector, right, and you have, let's say, a plane that is perpendicular to that vector, and you have 2 points like P1, P2, you can just project them on this axis. So that projection will give you like the length of that. It would be either positive, in that case you say it's a 1, if it's negative below, it's a 0, right? So that's the way to encode. As simple as that. Any random vector, project on that, it's positive, make it 1, negative, make it 0. You can use it to encode data, right? In this graph, what you see, so I have like 3 random vectors, H1, H2, H3, right? So the region in red, I can simply just see it is basically right of H1, right? So blue line, it is right of H1, I call it 1. Left of H2, call it 0. Right of H3, call it 1. It's called 101. So that's like just way of getting the region number. So I divided the universe into regions. So those regions are just based on these random vectors. So we are segmenting the space into sections. So now you get a new vector. You just do 3 dot products, know the region, right? Now you can scan only this region. So let's say, for example, you left out 90% data. Now you have to scan in this 10%. So this way, it kind of saved you. You're searching in a million space from just like to 10,000. But to do this, it had to compromise a few things, right? So because these vectors, they use projections, and these are like approximate vectors or like pseudo random vectors. Don't tell you the math, skip the math, look at the last line. There is some formula which says you can choose a lever, right, which gives you either more precision or more search power. So you can look at the formula later on, but essentially it is a tunable property. So all these vector stores have some algorithms which can be tuned between speed and accuracy. So that's, I would say, like a trade-off you have to make between do you want more speed in your system or more accuracy. So I'll talk about one more derivative of this called ALSH that is used by Google, right? So they use the same system LSH and modified. That's called asymmetric LSH. So just to give you an example, right? You have like 2 points, right? X1, X2, and they're like 2 centers, like region zones, C1, C2. I want to map it to, right? So normal thing they project, right? X1 to C2 and X2 to C1. So these are like projections of these Q1 X1 bar, Q2 X2 bar. if you look at this diagram, right, uh, these green and blue, right? So qx1 bar is more than qx2 bar, but in reality, the real points qx1 is less than qx2. When I say less, basically I'm looking on q. Basically, looking at the position of the point on the q, like on this axis. Are they far or closer, right? That's greater and smaller. So the projection says they are far apart, x1 and x2, but in reality they are closer in the real projection line. So what these guys did, they said let's take the direction also of the query vector and take a projection, right? So now if you do a projection like this, now basically, yeah, they got the right order. This is like a small operation these guys did in Google to bring this algorithm, and this is part of, let's say, the scan-n product. So this is like a graph of different products. So like this was given by Google, that's why Google is on the top. So there are more products out there, don't worry, this is not the best one. But scan-n, right, is optimizing on speed and accuracy both. So I would say look at your vector store metrics, right, how they're trading off between your accuracy and speed, and choose the one that works best for you. So these are lots of plots, benchmarks happening over there. I'm not recommending a tool, but I'm saying just look at these things. Because it's benchmark done by Google, you'll see Google on top, right? Some other company will show their product on the top. But check for these kind of metrics, the trade-off between these things. So I would say, like, in your real data, right? So you have these different chunks out there, yeah. So you want to do like, I'll just quickly say all the points over here that you want to look at. So to see the accuracy, you should basically kind of look at a full scan, right, versus your optimized scan. If let's just make a mistake, in that case, it will miss out some queries. Let's say you want to look at 100 documents, do a full scan of 100 as compared to like using the vector DB. If they're making approximation, you'll kind of miss some documents. So that difference is your accuracy issue, right? This way you can kind of measure how good is they're doing. From a similarity function, so the popular distance, right? Is that a good metric? Not really. So because the distance tends to be like far apart in high dimension space. The statement looked weird to me also in the beginning, but yeah, it is kind of true. And that equidistance is not a good distance metric to see the, I would say, distances in the high dimension. To give intuition, you can do a small test, right, to prove that. Take just two dimensions, like random points in any two plane, and create data synthetically. Like for example, add like a noise to x, small epsilon Gaussian noise, and keep adding more dimensions. Like I have two dimensions, x and y. I can like create a 3-dimension just copying x plus epsilon, and like again x, x, x. So actually I'm just copying x with some noise into multiple dimensions. The same data, there is only two independent vectors, I'm just keep adding them. And just compute distance matrix to see like the distance in all these different dimensions. If you just plot them, this like a plot of distance, right? This is a 2D plot in 3D, 4D, 5D, 6D, 7D. In each of these plots you can see the width is increasing, right? And the mean is shifting. So actually, these distances are increasing. So I did not add any information. I just copied the dimension, right? So in reality, it's kind of the same data, but in new dimensions. But what you perceive, these points are far apart. So that's why it's not a good distance metric. Cosine, yeah, that's good because that's an angle. It preserves distances, so it's a better thing. But is it the best? Not really. It's a complex topic, so I'll leave that over here, and that can't be covered right now. But yeah, that's good to start with, but that's not perfect also, right? It has some flaws. I'll again talk about the data type, right? So over here, there are two things. So like you can use a chunk rag, right, or a graph rag. This is like a news article on two movies like Barbie and Oppenheimer, which came last year. So this article says Barbie is doing better than Oppenheimer. So this is like a chunk. I can use my query on a chunk, or I can compress into like an ontology, right? So the same thing you can store in a graph, right? You have like the edges. Like Barbie is enjoying super low overseas, right? Barbie has amassed $528 million. So you can compress information into graphs, right? So that's like another way of storing data. So again, graph rag ontologies is a complex topic. Just want to give you like a pointer. So this is a entire thing itself. I'll just leave it right now and won't go deeper into it. So now I come to how you can basically improve performance, right, of the rag system. So you just right now, I'll just summarize. We looked at the embedding quality, the vector index quality, and let's say the similarity function and data type. How you can look at what's working, not working over there. Now, how do you fix it, right? For fixing. So the first part, this is the three key parts, right? You have a query, embedding, retrieval, right? Very, very high level. So how do you improve each of them, right? So you have three areas to play with. Play with the query, embeddings, I told you earlier, right? You can look at the best embedding model for you, and retrieval. So query performance. So one way is basically query augmentation. You can add more to query, right, to maybe maximize your search possibility. So one is basically adding more like possible answers. Like for example, what is the company's future? You can say possibly companies doing good, adding new revenues. So you can use domain knowledge, right, to add sample answers, or maybe use LLM, right? Ask them to generate hyperlink answer. This way, probably your context or question itself will have more answers, so the search will get better. Second is you can actually augment with multiple similar questions, right? So that your search performance increases. Again, one option domain knowledge, second option LLM. So this way, what you're doing is basically the same question for the search purpose. You're actually adding more words in that context to make your chance of your matching better, right? Either by adding a hyperlink answer, which you believe could be a true answer, so your embedding will get closer. So this basically just a seed to make embeddings closer, right? So that you can get a better retrieval. So that's like one way of query performance. Second, embedding model side. I told you how to debug that using manifolds, but how do we fix it, right? So there are 4 types of these encoders, right? I think encoder you already know, the default ones, that's BERT. Then you have the sentence one, that's called the Bi-Encoder, right? I showed you earlier sentence transformer. That's one. Then something called a Cross-Encoder, right? It's like a classifier. And then Dual-Encoder, that's a special one coming from Facebook recently. I'll talk about that. So at a high level, like a Bi-Encoder basically is using like a Siamese network. That means it takes a couple, right? Sentence B are the similar. So while training, they actually look at similar sentences and like the different sentences. So it understands from the beginning that what is good, what is not good. So you take one model, get embedding, another model, take embedding, right? And kind of then it's like a shade. They looks like 2 encoders, but they're common, right? It's single encoder basically. So with this kind of architecture, you can, let's just generate similarity, like cosine similarity, and have ground truth. That means somebody labeled that these sentences are similar or not similar. Then give a score, right, between 0 to 1. So you can use like a mean square error, right, on simple thing. What is your true similarity between your perceived similarity between the function? So delta between that will give you error, and you can tune. A simple way to basically get a Bi-Encoder, right? So, but for this, you have to label, right? That's the problem. How do you label so many sentences with score, right? This is score 1, score 0.5, that gets harder. So although possible, but the process is, I would say, more cumbersome. So there are smarter ways to train Bi-Encoder, right? Like this example, like you have to give this like S1, S2.3, S1, S3.7. So you have to give those scores manually. So to assess that is not easy. So although you can, if you have that, very good. There is data called STS benchmark. It is available on internet. You can use that to train model. But for a domain, if you can do, well and good. If you can't, then there are more smarter ways. So the other way is using something called contrastive loss or the triplet loss, right? So idea is you have like a pair, like an anchor sentence and a similar sentence called positive, right? For example, you're going talking about detail on the detail sentence, talking about product on the product sentence, like a negative one, which is basically different format. So from these, what you can do, again, get the embeddings and like get some similarity, either Euclidean or cosine. So I'll take 2 variations, like one triplet and contrastive. Let's talk about triplet first. In that, basically, you need like a pair of sentences class. Like look at below, like S1 is sports, example, S2 travel, social, food. I just need categories, right? Example sentence and the category. If you can generate that, that is good enough to train this kind of model. It uses like a loss function. They basically maximize the anchor and positive distance. That should be higher. Negative would be lesser. Just simple objective. It will maximize on that and give you like a model. That's one way to train it. Second is called contrastive loss. You need like tuples. So like anchor, like for example S1, S2, it's either positive or negative, right? So every sentence you take anchor and the negative positive sentence until it's negative positive. With this kind of set, you can have a function, and that's like the function of that. Leave the maths, but you can find it in Google. But it basically maximizes the similarity of the positive with negative ones and gives you a model. So this is actually like a very powerful model. Remember the first plot I showed you, like the confusion matrix, the black plot, it was sentence transformer. It was working better in GPT 3.5 because this was a Bi-Encoder. So actually we believe these are commercial LLMs. GPT is definitely great. But for encodings, I think these are more smarter models. So Bi-Encoder is much powerful. And as you saw earlier, it was covering more range. It was covering from 1 to 0, and it was having a more distribution, more separation. So I would recommend definitely go for Bi-Encoders. That's like one of the great things we have. Second is called Cross-Encoder. It is better than Bi-Encoder, but it's hard to train because it's a classifier, right? So you have to say a sentence A and B, is it 1 or 0? So for that to train, you have to basically create like a loss function and make a model. So the idea is it's hard to train such a model, right? It is much more similar because it looks at your exact data and gives you answer, right? But answer is not a embedding. Answer is like a 1 and 0. So that's why you can't generalize. It can't make a vector DB of that. So this can't be used for vector DB. So that's why people use them for to re-rank it, right? So like this is a normal RAG model. So we kind of use to get vector embeddings from, let's say, Bi-Encoder first. Then we can use a cross-encoder to re-rank the rankings. So it will again take the output of the first function, right, retrieval, and give a score again. So this has proven kind of more powerful than the regular methods that we have. So this system is kind of a more optimization of RAG, which kind of works much better. So you will find on these, like in many open source tools, if you look at like in Google, they use these systems on the backend to improve the efficiency of RAG. So this was basically about RAG and things coming in. Now the next part, Dual-Encoder, right? Remember I was telling you that in the MDS plot, the question was different from the answer, right? But what Facebook did, they made like two encoders. One called question encoder, second called answer encoder, right? And now they are two different models this time. They're not similar. They maximized like the embeddings of these two to get like a two models, right? One question model, answer model. So I'll show you an example to see how they're different and better than them, right? So how to use them basically? To use them, what you do, you kind of, while indexing, use the answer encoder to index data, right, in the DB. But while retrieval, use the question encoder, right? There's a link, I think you'll find in Google for the Facebook. So this is like a different way of doing a RAG, but yeah, it gives you like a more efficiency. Give an example, like these are sample questions answer, right? If I look at sentences, I can find the similarity of them and see how they're different and easy. If you observe the question, I've copied into answer also, right? Exactly. If I have same embedding model, I'll get similarity exactly one. So in the first case, it's like a regular sentence transformer. You can see like the first, second, third, they're exactly same. You get a very high score. But the same thing when done via dual encoder. See, the first sentence was sent to question encoder, right? Not to the answer one. So the first, second are exactly same. Still the score is lower. So that means exactly same sentence, character by character, is different because they're different encoders, right? Because understand that is a question and it's supposed to be matched with an answer. So it is smart enough to just not look at the meaning, also look at the context. You want to do question answering, right? So that's why for question answering purposes, your better answer is the third one, like the biggest context is Asia. So it gives a better score to that. So these are like more smarter ways to encode things for them. So yeah, so like you can also get like feedback from humans, right? So you can get feedback from humans, like from LLMs to see is your RAG doing good or bad. So that's another way of basically incorporating the feedback. So let's say somebody reviewing your retrieval and say this is good or bad, like thumbs up, thumbs down. You can again train a model called adapter matrix to basically use that. So let's say you have these multiple vectors, your query and document, give a score, right? Was it good or bad? And from that you can let's create a loss function, train matrix that's called the adapter matrix. That how you can bias your basically embeddings to tune towards a use case. That's like customizing your own use case. So in usage, basically, you kind of, it's like just transforming the vector side. It's just changing it. That's the way it works. Just a simple technical thing. Doesn't matter much. But the point is you are tuning it to your own domain need. So that's a way of basically tuning a RAG to your own business data. So that was all about RAG, right? So that's the output, like the red ones were the previous one, green the new, right? They were far apart earlier, now they're very close by. So this takes care of those kind of domain-based tuning. So with this, I think we wrap up the RAG part. So now we have LLM side. How do we look at LLMs? How do we debug LLM? So the key part is, like if the answer went wrong because of the LLM, but the RAG was good, right? So now how do you debug LLM? That's the difficult part. So now we need to see that probably inside the LLM something went bad, right? So the something went in the context that was not good. All that was all right, right? So how do you avoid LLMs? There are like three key ways. One by humans, right? You can say answer is right or wrong. Second, you can use another LLM to say is the answer incorrect or correct. So third is called LLM-Diagnostics. So these are like ways to debug it. They are less popular, but they are also very useful. So the key idea is you are like doing a trade-off between your precision and kind of its generality, because human side can do a great job. They can tell you is it like exactly what you're looking in your domain knowledge or not different, right? But you can't scale with human side. You need to lots of humans to label data, but LLMs can scale easily. So how do you balance them? Actually, you need both of them. So, but you should see what your task is, right? Is it an objective task or a subjective task? I'll give you an example. Objective means like entity classification, right? Or status analysis. These are clear tasks. For example, I want to look at the name of hospital, like, or my drug name, disease name, right? Or my biomarkers. It's a very clear question and kind of getting me the exact entity. So I can do it like the traditional way, make like a ground truth and measure it. So for these cases, we should go classical way, find the prediction and the actual answer, and do like precision recall F1, because that's the way to judge them, right? So this works, but the key part is these system helps in it, right? So how do you check for that? I would say run the same thing again multiple times, and even at temperature 0, it will help with it. So if you run multiple times, right, then you can take random samples, run it again. If your answer is changing, that means it is not stable, right? So there is something issue. If you look at like the standard deviation of variance of the answers, if that's increasing, that means your model is not good, right? You want like a stable model. So you want to go towards like a non or like a zero variance model. That's the best one for you, the most stable model. So for object tasks, I think measure the variance. That will give you the way to kind of see is it a good or a bad model. Now coming to these other like subject tasks. If subjective means you are doing like a summary, right, or a Q&A or translation. So you can't like have an exact answer, right? Because they're subjective. There is no exact answer. I can do a word matching, right? But still I can do a partial matching. So there are things like lexical matching. The words still be similar, right? The number of words they are mostly matching or not there. You can do something like a rogue score. That's like takes a unigram, a bigram, right? These words and match how many are matching, right? So this course gives you like some idea how close this with like two reference answer. So basically you compare it with answer given by human as given by the LLM. And kind of, again, you can do like precision recall, so you can quantify. So idea being, the moment you can quantify things, right, you know it is right or wrong. But if you just look at the answer, it's hard to judge. So get quantification in all your, I would say, tasks, be it objective or subjective. So other way is semantic relation, right? As you know, embeddings are powerful. So you can see here also that the question embedding and the answer, are they close by or far, right? The same thing. If this related, they would be nearby. If they are not nearby, it made a mistake, right? Or hallucination. So that's another way of looking at the answer. Is it like right or wrong? So these are like two ways I was called lexical and semantic. One looking at the words, second looking at the meaning to judge are they kind of doing good or not. So yeah, you basically want them close by. So I like talk about like two things, right? Main, how to judge LLM using LLM and via LLM diagnostic. So I'll spend less time on this because there are lots of tools out there, right? That how you can like judge LLM by using LLM, like index frameworks. You can use like a reflection framework, like a reviewer agent, and like maybe a main agent. So that's easy. But the essence being, you need to capture three things, right? A context relevance. That means is your LLM getting the right context? So you should define a score for that, right? So get me a score for the context. Is relevant for the current question. Then relevance for the answer and for the groundedness, right? So these three criteria, if you can measure, get a score for them, then you can know that are you doing good? Like is the answer related to query, right? Or is the RAG output, the context relevant for my question? Similarly, is the context given by RAG relevant for my basically answer? So this way, these three things, if you can measure, that will give an idea. So you can make prompts for them, right? So you can make a prompt to judge context relevance, answer relevance, and groundedness. So just show you the output from one of them, right? So you can just score from 0 to 1. So like this was a question, which field has the most exciting carrier opportunity, right? It gives some answer. So how do you know was it right or wrong? Based on the RAG. So this is like from the LLM, I made 3 prompts like based on 3 things and asked the LLM to give like a score between 0 to 1 for all these things. So it's saying it's like a good answer and it's like relevant also. As you can see, it makes sense. So, but like other question, right? So this like is talking about, so was a more vague question. So it's saying what are the avenues? It's talking about maybe doing projects, all those things. So it's not really that closer to what we're asking. Look at the scores, you'll see, right? Relevance goes down. So you can easily look at that, is it doing good or bad? So you can easily quantify it using these scores to see is the answer good? Is it grounded from the evidence or not, right? And again, like another example, it's a big answer, but it can tell you that it was a good answer, relevant context, but was not supported by the RAG context, right? So like these are ways you can easily see how is it working well for you or it's not working well for you. So I think it's not hard. There are lots of tools out there to give you a score easily. I'll give you like example, like for a text summary task, how can you give scores on 4 criteria? For example, I want to look at is my passage is relevant, fluent, or coherent. So I can easily make some prompts. So it's like a template, right? Just say evaluate these things. I'll give you a criteria, the steps, right? Document the summary, and we are giving like 4 categories to kind of judge it on that. So these are like prompts, I think. So you can look at them on Google. It's easy. I'll just skim through because it's easily available, right? So, but these are idea. Using these prompts, you can get scores, right? It's simple text. I'll just skip through, not important. But I want to come on the next part, right? This is, I would say, more important. It's less talked about. How you can debug LLMs, right? So there are tools in GPT, right, where you can look at what's happening inside. So there's something called a feature called log probability, right? It's not used too often, but it's available, right? It came in last year in GPT. So you can get a probability, right? So when you make your function, there is a field called log props. It's by default off, right? You can set to true, and kind of when you create a client, so this will also give you the probability of token along with the answer. So now this can actually let you quantify, is your answers going good? Is it hallucinating? Is it certain, uncertain? So you can use this diagnostics using log props to get that. I'll show you like 4 use cases how to use log props and debug it, right? So first one is like a classifying problem, right? I'm asking you to classify a sentence into like 4 categories: physics, medical, maths, geography, and history. So there are like 4 sentences below, right, which are kind of there. One is very clear, second slightly vague, third confusing. So I want to see how we can judge the performance of the model, right? So the first one, right, it says quantum mechanics is physics, right? 100% confident. So, and just to let you know, so you can convert log probability to normal percentage by this formula, right? Just raise to power e into 100. So that's easy. Now, second example. So like this is a terrain on Western Ghats. It is also clear, right? It's talking about geography. So it is confident about that highly. Now this is like more slightly confusing, right? It's talking about trajectory, but also about equations, right? So it's part physics, part maths. So it says majority maths, 89%, 10% physics, right? So it shows it was not fully confident on maths, right? This will not get to know if you just look at the answer only. So these additional things are telling you the confidence, right? Similarly, let's say the last one, right? So the Aryans cross Himalayas. It's history also and geography also, right? So it's again the same thing. It is 4% geography, 90% history. So the key part is with this additional log probability, you can judge is the LLM sure or not sure. So this gives you diagnosis, right? So any answer you can kind of get these numbers to quantify. Like in traditional machine learning, right? We have this confidence score probability, right? So we lost those things in GPTs, but you can get that back using these log prob. So I would say if you use these things, it will be better to debug. Similarly, the other use case, right? How to check hallucination. So it's like a simple prompt again. So asking a question and kind of just asking you to like summarize, right? So I'm asking like before answering the question, tell me, do you have the context to answer the question, right? Giving the article in the question, whatever question doesn't matter. So like this is some paragraph, again the same, I picked the same example, right? The news article which I picked earlier, and asking questions, right? As you know, this article is about the Barbie movie, like earnings. The question I asked was like different, is Barbie going to France? It is talking about the Barbie character. That's not in the article, right? Was Barbie happy? Again, not in the context. Like third is like relevant, right? That's a clear question about the article that we can do. Yeah. So in this case, if you look at the probability, right, the first question it says is 65% confident, right? For the second, it says 70%. Although it is saying this is true, right, that the context has answer. It seems tricky, but I'll show you how it's saying that. But in the first case, very clear. It says false. There is no context to say did she went to France or not France, right? That's kind of correct. Similarly, for the last one, it knows basically to compare those movies based on the earnings, right? So that's good. So the first 3 are very clear, right? That you can use the LLM itself to quantify it. Do you know the context? Is it good enough or not? So this you can use that. So you can also find hallucination by token level, right? Instead of looking at the answer, look at the sum of all the answers. I found the same thing. I expand the same answer into words, right? So like these answer, the blue is the answer, right? The green was the question. Answer is no, Barbie did better than Oppenheimer, right? So for each token, I get a probability again. So I can from these look at even token level confidence, right? Is each answer word irrelevant, right? Similarly, second question, right? It clearly says the article does not contain mention about the travel to France. So that's a good answer, right? It says it's very sure it has no information. But it says Barbie was happy, yes, right? So that's tricky. It was article about the Barbie movie. How could it guess it is kind of she's happy? So we can look at by expanding this. So now I'll basically define using called uncertainty. It's a very simple thing. Just take a mean of probability. As simple as that. Nothing new. So the mean of all the probabilities tell you what's the total answer confidence. So I have the same question again. This time I'll ask to give explanation, right? Last time I just told it to give the answer only, and then it just gives answer. This time, so for these cases, right? So we can see, even first is easy, right? But second part, it says because it can be inferred, because it got good earnings and she would be happy, she will be doing a party, so that's why you can infer she's happy, right? So the answer was still logical. That's why LM said the context is good, right? And it was able to get that. And uncertainty is, let's say, low here but high over, right? So you can measure, although answer is good, but it's uncertain. So these metrics can help you kind of get these details and how things are working, right? And I also like this end with like some tips to improve the performance of LMs. I'll just list all this down, and with this I'll wrap my session. So we say the key part is ensure we get the right context, right? That's the first part. And in case of every task, measure, I would say, by giving examples so that it knows what you're looking for. It's very clear, the task, right? And break into smaller problems. Like your bigger problem, bigger problem, break into smaller chunks and give it like task by task, right? And you can use multi-agent, right? That's also there. Or you can use like framework DSPR, right? So all these can help you get those things, and you can always debug, right? You have those tools to debug what is working, not working, and kind of you can make it better. So with this, I just wrap up. Thank you very much. Yeah. Any questions? Yeah. Yeah. Like basically a probability, right? So probability is telling me how confident the model is about the token. So basically average of all the probabilities. So that means if it was unsure about each token, in mean average was unsure, right? Word by word. Word by word, exactly. Yeah. Yeah. So that's a simple way to define uncertainty. Yeah. 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 But they're conditional, right? So is A in itself is not always like bringing on neighborhood. They'll change, right? If the word is A is relevant in the neighborhood, then you'll get higher score, lower score. If you look at in the previous case, the Barbie yes dot, the dot was what probability, right? The probability dot was changing, just a stop word but changing. So different context changes. So in short, they're relative also. So same thing applies for them also. Relatively, they'll keep changing, and you can change them also. Yeah.
We will take the last question there, so please go ahead.
Yeah.
So when we are looking at uncertainty, it might make sense to look at both the mean of the absolutes as well as something like a Shannon entropy or
Exactly, yeah.
normalized value to get a sense of whether there are some very relevant tokens.
That's a good idea. That's a very good thought. Actually, thought about the same, but I did not mention entropy because entropy takes about diversity, right? So that means high entropy score would be how diverse are the tokens. Ideally, I want them coherent, right? So that should not happen. So ideally, you won't get high entropies for answers, and this is a very bad model, right? So normally, mean will get you a sense. Entropy would be near about the same thing because they're related, right? As he was asking, like a word like is A, but also have a same probability as the neighborhood words. So kind of they'll flow through. So entropy, yeah.
There will be some words that are very relevant.
Exactly, yeah.
High mean and a low and a high entropy.
It will be basically like fewer driving. Basically, if they're in a 10 words, 2 are driving the score more than high entropy, right? But ideally, yeah. So ideally, you want basically all of them to drive, right? Basically, a good answer will have all relevant tokens. So that's where, yeah, mean gives you idea. You can, but that's a good idea. I think I totally concur with that.